A little bit of a demonstration and a little bit more water in here. And I'm going to take a drop of food coloring and I'm going to just put it in here and everybody see what's going on. Now, we could sit and watch this for 28 minutes, I guess, but that wouldn't be very productive. So let's fast forward to what this is going to look like in about a half hour or even less, and it'll look like this because I did this one the same way a while ago. And so what difference do you see between the two? That's fairly simple. Just look at them and what can you say about the two? Tyler Hobman, what can you see? What difference can you see? Okay, excellent. All right. So in this one, the food coloring molecules are all grouped together, and in this one, they seem to be evenly spread out. And so the question is, and if you can answer this question, then you'll do very well on this next part. The question is, what causes these grouped together molecules to be spread out? Why do they do that? Do they want to do that? Is that their plan? Is that their goal in life? Or is there something else? What is causing, as this very moment as we look at them, what is causing these ink molecules to spread out from each other? I'm going to ask you all to think about that because I'm going to call on some of you. Jake, are you here? Jake, what's going on? Why are these things moving apart? Or let's put it this way. Why aren't they all clumped together anymore? Over here. It's a fairly simple answer. There's no profound scientific principle here. Makes you feel even worse than if you don't know. Let me ask you this. If we cleared the desks out of the room and I took the whole class and clumped you all together right here and said, don't move. And I came back a half hour, and if you did what I said, would you still be clumped together? Yeah, okay. So what would have to happen? What would you have to do in order to not be clumped together anymore? Jake. Move. Exactly. You would have to move. All right, and so that really answers the question, why are these spread out all over the place? It's because the food coloring molecules are
spread out.
Moving. All right, they're moving, exactly, they're moving. And I think you learned somewhere along your career that all molecules are always in motion. You learned that? Are the molecules in your desk moving right now? Yeah. All molecules are always moving. When it's a solid, the molecules are vibrating just a little bit. When it's a liquid, they're going longer distances. And when it's a gas, they're going long distances. Okay. So that number one. Why do these molecules disperse? Because they're moving. And when they move, they bump into each other. That's the second one. So first of all, the food coloring particles, molecules, are moving. And secondly, when they move, they bump into each other. And when they bump into each other, they bounce off and go different directions. And so here we have a representation of it. Here's the drop of ink with all the molecules. And the molecules are moving around. And let's take a look at two molecules. Let's take a look at this one. We'll make them big. And this one. And let's suppose they are moving towards each other. When they hit each other head on, they're going to bounce opposite directions. And this one is going to end up over here. And this one is going to end up over here. And then they're not going to be there anymore. And the droplet of ink has become a little bit less what? Think of the magic word. After those have hit each other and they've gone opposite directions, now the drop of ink is a little bit less what, Amy? Amy? A little bit less. Excellent, you got it, exactly. A little bit less concentrated, right? All right. And then another two are going to hit each other. And so we'll put one over there and one over there, and we'll have to take two of them out for that. And then we'll put another one, two other ones hit each other, and so we'll have to take two of them out for that. And then another two hit each other, and so we'll have to take another two out. And you see our droplet is becoming dispersed. It's becoming less and less concentrated because the molecules are spreading out all over the place. All right. Easy enough to understand that? Okay. All right. Now answer this question. Do you think it's possible that any of these blue dots that have been dispersed would collide with another blue dot? Is it possible? Sure, because they're all moving. Is it possible that one of them might get bumped back into the center? Sure, it can happen, and it does. Yet, there's far more moving away from the center than towards the center. We can represent that with vectors, a little long arrow indicating that more of them are moving this way, and a short arrow indicating that some are moving back. And here's the important question you need to answer then, and that is this. Why are more of them moving away from the center? Okay, again, I'm going to ask everybody to think about that. Why are more of them moving away from the center of the drop than back towards the center of the drop? Brantley.
Because there's more collisions happening in the center.
You nailed it. You said it exactly the way I would have said it. There's more collisions happening here because there's more molecules here. So where you have a higher concentration of molecules, you're going to have more collisions per second. And so if you have more collisions, there's per second here, there's going to be more getting thrown out of the center than back towards the center. All right, very good. So what we have here is a high concentration of food coloring particles, and out here we have a low concentration. And this arrow represents a net movement. Net means if you take the number going this way and subtract the number going that way, what do you end up with? Well, you end up with a net movement this way. That's why we drew that arrow longer. And so the net movement is always from high concentration to low concentration. We say that it moves down the concentration gradient. So a net movement is always going to be from an area of high concentration towards an area of low concentration. High to low, that's what we mean by down. It doesn't have to physically go down towards the ground. Down simply means, down the concentration gradient simply means we go from a high concentration to a low concentration. All right, now just out of curiosity, is this all new material or have you had this in ninth grade? I don't know what's going on in ninth grade. Have you had this concept or not really? Kind of okay, I'm not sure what that means, but kind of, sort of, but, all right. Okay, so then we get to the, to this, where eventually we end up then with the concentration being equal all over the place, and that's what we have over here in this beaker. And we say then that we have reached equilibrium. Where there is no concentration gradient anymore. The concentration is equal all over the place. And we can quickly show this with a little animation. Start over here. We have a high concentration. Here it's low. You'll see over here there's more collisions per second over here. So as a result, there's a greater chance of more of them going this way than back the other way. Eventually we reach equilibrium. There's an equal number on both sides of the beaker or everywhere through the beaker. And then we're going to get just as many going that way as back the other way. So that's equilibrium being reached. All right, so what topic is it that we're talking about? Anybody know? If you had to put one word on this, if you had to give a title to this, what would the title be? Starts with a D, in case you're thinking maybe. Jake? Diffusion, good. So the topic here is diffusion. And so let's define diffusion. Diffusion is the random movement of molecules. I suppose it doesn't have to be molecules. It could be people. It could be baseballs or whatever, but we're talking about molecules here. The random movement of molecules from an area of high concentration to an area of low concentration. So it has to be random. There can't be any intentional movement from one way to the other. I used to do this as a demonstration in class, and we'd move all the desks out of the room and we'd blindfold everybody and break you up into a couple of groups and have a bunch of people over here and just a few people over here. Spin everybody around and say, okay, now start moving. And when you bump into somebody, just gently go the other direction, and we'll see once if we can reach an equilibrium. Well, it never works, and it's the guys who can't do this thing because they hear one of their friends someplace and they just kind of make a beeline for them, even though they're blindfolded. They're bound and determined to smack into one of their buddies. And so there was no randomness involved in it, nor was there very much gentleness. So anyway. Okay, now, that's all pretty simple. Let's add a little bit level of complexity to it. Let's take a container and let's put a dividing line here. We can put some holes in here if we want. And let's fill this container up with water. Now, I can't obviously draw every water molecule. I wish I could because it makes it a little easier to see what we're doing. But we're obviously going to have the same number of water molecules on each side. Not to draw them so dense. Okay. So we have an equal number of water molecules on each side, and they can flow back and forth freely. All right, now let's take some sugar and dissolve it on this side. Now I think you know from physical science or someplace in your schooling that you can't have two particles of something in the same place at the same time, right? You can't, matter takes up space. So if there's something already there, you can't have something else there unless you bump the other thing out of the way. And so we can't have sugar and water in the same space. And also remember that every space will be filled up with something. I couldn't fill every white space on the board because it would take too long. But the idea is that every space is filled. And so let's call this side of the container A and this side B. Which side, A or B, has a higher sugar concentration? Austin? A, okay? Everybody can see that. There's a higher sugar concentration on this side than that side. Here's the one that's a little trickier. Which side has a higher water concentration? Tyler? B. Does everybody see that? It's really important that you see that. And in fact, it's so important that maybe I ought to illustrate it. If I take an area here of, I'll make an equal area on both sides. I should have done that. Should have made it a little different color that you can actually see. All right. So we take equal area on both sides. Does everybody see that there's always going to be more water molecules in this rectangle on this side than there is in this side? Because there's always going to be some sugar on this side. And if you could have, let's say, 1,000 dots in this area, all 1,000 will be water over here, but less than 1,000 will be water over here because some of them will be sugar. Because you can't have two things in the same place at the same time. So it's either going to be water or it's going to be sugar. It can't be both. Does everybody see that? So the water concentration is higher over here on this side. So in which direction will there be a net movement of water? From A to B or B to A? All right, so everybody see that there will be a net movement of water from B to A. There will be some movement of water from A to B, but there will be a greater movement of water from B to A because of our definition of diffusion. Random movement of molecules from an area of high water concentration, in this case, to an area of low water concentration, in this case.